All right, students, got a question here about the torque from a motor. So this is a good one, and your author does a good job of deriving the equation. So let me encourage you to look over his work. And let me just explain. The tau is the torque, the same symbol we used back in Physics 110. Here's the number of turns in a loop. So you might have something that looks like this, where the current comes up and goes around and around and around and around and around and then back down. And then maybe there's a magnetic field. I'll just make it left to right. But see, this current going up, if I use the right-hand rule, would put my thumb up. And if I put my thumb up and my fingers towards the magnetic field, I get a force that's in. And over here, I'd get the force that's out. And that's going to then twist this, and that's where the torque comes from. So this gets mounted on a little axle, and so that's the basic properties and operation of an electric motor. And so this N represents how many turns you get. I is the current in this motor. A is the area, so how much area, which kind of makes sense because you would have this dimension, which is how much force per length, but you would have this dimension, which is the lever arm in your torque. So the combination of those two come out to be area, and then the strength of the magnetic field, and then the angle. So if we just take the derivation as complete, this is pretty much just kind of a plug straight in and calculate type of problem, because it says, what is the maximum torque? So since the sine function can vary from -1 to +1, the biggest it can ever be is 1. So that's at 90 degrees. So taking that to be the position when it's at its maximum torque kind of reduces that equation right there. So what is the maximum torque of A? And it says 150 turn square loop of wires with 18 on its side. So under area, I'll put 0.18 meters and square it, which carries a current of 50 amps and is in a 1.60 Tesla magnetic field. So putting in our numbers and also our units, but I'll start with our numbers here. We have 150 times 50 times 0.18 squared times 1.6. And so I'll call it 389. And then if you look at the units, we've got an amp times a meter. Now remember, the definition of a Tesla is the amount of force you would get per amp per meter each second. Okay. Sorry, Newton per Coulomb, that's what I meant. Yeah, so newtons per Coulomb meter per second. And then, of course, looking at this is kind of where I was jumping the gun, is a Coulomb per second right here. These two is an amp. And so, oops, I forgot to square this up here. So this would be meters squared. So we've got an amp here, a meters squared, and then the Tesla, which is great because the amps cancel off and one of the meters cancel off, and you're left with Newton's meter in the top, which is exactly the unit you want for a torque. Okay. Then part B goes on to say, what would be the torque when you are at 10.9 degrees? And so instead of me putting all these things and working them out again, note that that's just going to be the same number, 189. So then I just have to multiply by the sine of 10.9 degrees. And so I guess we're looking at a pretty small amount of torque of 73.5 Newton meters. All right. Like I said, a little more plug just straight into that one. All right, hope that helps.